So here's our next Coriolis problem, which is another, this is more of a carnival problem, though large amusement parks will have variations on this. So see if this ride looks familiar to you. Okay, I have this platform here, and so it says here it's going at 1.5 radians per second constant. So it's going like so. No problem. And on top of this platform are these buckets. People would sit in the buckets. So, and here we have, so here's a given bucket, and this bucket is turning relative to the platform, not ground. Relative to the platform, this is turning at 2 radians per second. So if you've ever been in one of these rides, it's basically this is turning, and then you're in another thing that's turning at another rate, and when you line up on the outsides, you get squished. Okay, so hopefully that's rings some bells, and you haven't been sheltered in your life and have gotten to do this thing. It's always fun to do this with your parents and then try to extra squish them on the outside. Of course, then they go to squish you, but it's all fun. All right. So what do we have here? Here's the center of, this is like a merry-go-round with other merry-go-rounds on it. So from the center of this base out to the center of the buckets that are spinning, it's 3 meters. All right. And then the bucket radius is 0.75 meters, and people would be sitting in there. Okay. So let's see what we have. I want to figure out at this point B right here, what is the velocity and what is the acceleration. So let's think about that. There's a point B on the base, the merry-go-round as it were. So it has a velocity and acceleration. But then up above it is this bucket, which I'll call link 3, which is also moving, so it's going to have its own separate overall velocity and acceleration. So what we're going to do is we're going to go from this center point P out to B on link 2, and then we'll use Coriolis to jump to B on link 3. Okay? Because if you think about it, this point B is not always linked to the point B here. So the person who's sitting there, they are effectively touching or shadowing link 2 in this path. Okay? So, but the merry-go-round is always touching them through their feet, or if they're sitting, their butt, however you want to look at it. Okay, so B, person sitting here is getting effectively touched, as it were, from the thing below, all in one spot, but they're touching the merry-go-round in all different spots. So we know our link 2, we know our link 3, let's go knock it out. All right, so little free body diagram just to keep everything in perspective. So here's the base, link 2, 1.5 meters per second, and then here's the bucket that's spinning even faster at 2 radians per second, relative to the platform. Not relative to ground, relative to the platform. And as we get out from P to B, we're going to go out 3 meters to get to the center of these buckets, plus 0.75 to get to the B point we want to analyze. Now, this is useful to view from the side. Okay? So, if you view what this ride is, you got this big, large plate that's the merry-go-round, and there's a motor here. And there's a hole in there where there's another motor that's spinning the bucket. And so when you look at how the B's are, you can very easily see there is a B on link 2 and there's a B on link 3. They are not rigidly connected, so we have to make a jump from this point to that point. That's Coriolis. Okay? So, let's knock off the velocity for this thing. So, to go from B on link 2 to B on link 3, what is B on link 2 doing? It's just nothing more than omega cross R. Omega 2 cross R from P to B on 2. So sometimes what people do is they'll actually put a little 2 in here. Okay, to emphasize what you're talking about. And then we have the relative velocity of 3 to 2, which would be, picture somebody lying down on this plate, the link 2 plate, and if they're watching B, they go, what are we seeing it do? And if you're trying to visualize this, the easiest thing is to picture somebody squeezed underneath this plate watching B. what are they seeing? If somebody could be lying down on here, but looking up at here, what would they see? Okay. Well, what they would see, if we just go back to B, so somebody lying on here, what would they see B doing? Well, they would be seeing B go, I'll just use the pen, going relative to the paper in this upwards direction. Okay? It would be going in the Y direction. It's spinning, but currently it's going to go in the Y. That's what they would see. How fast is it going in the Y? Well, that's determined by this rotation relative to the platform. So this is spinning, but then relative to the platform, this is spinning. And that's at 2 radians per second. So that would be omega cross r would give us the velocity of B on 3 relative to 2. And that's exactly what we have. So omega 2 cross to get to B2. So notice I didn't go out 3 meters. I have to get to B on link 2. So that's 3.75. Your instinct is to go here. You need to go a little farther. And then you jump from B on 2 to B on 3. So there's omega cross r for link 2. And then here's B3 relative to 2. It's the 2 radian per second relative to the platform cross r, 0.75x. And we can see that right here. Here's the 0.75x. Oops, got to move this up. Let's just say that one more time. 1.5x cross 3.75, that's the base, or the merry-go-round. 2 is how the bucket's turning relative to the merry-go-round. 0.75, that's this distance, because this is spinning. So we need omega cross r to get this VB3 relative to V2. Okay? Because this puppy here is spinning. Now it's just plug and chug. Okay, so here's all the numbers. Works out to B on 3 is 7.125 y meters per second. Now we have to do the acceleration. Let's get all this in. All right, so for B on 3, we start at what is B doing on the merry-go-round, which we could have figured out down, there we go. So we'll figure out what B's doing in the merry-go-round. That's just going to be alpha cross r minus omega squared r, when we see that right here. Now, we are told, going over here, the merry-go-round, the base, is going at a constant angular velocity. That means alpha 2 is 0. That term disappears. So we're left with minus omega squared r from P to B on link 2. All right, so that's minus 1.5 squared, that's omega squared, 3.75x takes us from P to B2. Now we have our Coriolis term. It'll be 2, 1.5x, that corresponds to the merry-go-round. All right, and then 1.5y, that was this piece back here, which we'll have to go back to that. All right, there was our VREL, and that came from here, 2z cross 0.75x. So that just pops over into the next problem. Okay, so there's that term. So we had the, that's radians per second. That would be, the units are meters per second. So there's the VREL. Now, we have to do, now the question is, what is the relative acceleration? Well, this is the same as we had on the last thing. So if you were watching this thing, you see this, it's spinning at constant velocity, but it's on a circular path. That means it has normal acceleration from B towards O1. Okay? So that would again be minus omega squared r. And that's what we have here. Minus 2, the relative angular velocity squared, 0.75x, the radius from B to 0. That's the radius of this circular path. So there's our A, B3, B2 rel to somebody who's just sitting here watching this thing go. Plug and chug, we get minus 15.9 meters per second squared x. Now, this was a kind of neat thing. We went out to this point here, and then we literally jumped to another spot above it. I want to note we could do this problem another way. Very clearly, we could do this problem another way. Note that when we did this, let's go back to this first problem a little bit. I'll just take it that route. All right, this omega was 2 radians per second relative to the platform, not ground. All right, everything we've done in the past in the course has been relative to ground. What if you were to convert this number here to not a relative angular velocity, a ground angular velocity? Well, you can do that really easily. What do we have? The base is at 1.5, and then this is 2.2 relative to the base. Add them up. So omega 2, or omega of link 3, if relative to ground, will be 1.5 plus 2, or 3.5. So let's just look at that, and that's what I have here. So now instead of what I did before, is I went from P to B on 2 and then jumped to 3, now I'm going to go via ground links, or ground perspective. I'm going to go from P to O1, okay, that's up here, and O1 is doing the same thing on both link 3 and link 2. And then I will go from O1 out to B, which is just what we did before in relative motion analysis. So that's 1.5. This is 2 plus 1.5. Now it's a ground reference. If I do that, VB3 is simply give me the velocity here at O1, then jump to B. So that would be omega cross R to O1, and then omega 3 cross R to B on link 3. All right, so that's 1.5 cross 3, not 3.75x, plus, now it's the bucket's rotating at 3.5 radians per second relative to ground cross 0.75x. Add it all up, get the same velocity. Of course, we can do the exact same thing with the acceleration, which is, we'll just bring that up. And since there is no angular acceleration here, the alpha cross r terms disappeared. So we simply need minus omega squared r to go out to O1, and then go from O1 to B with minus omega squared r, where r is from O1 to B. So the difference between what we're doing now is this becomes 3.5. Multiply it all out, get the exact same acceleration, as you should. So there are times you can actually get out of doing, by simply changing how your problem is stated, you can actually get out of doing a Coriolis. Or you can do it in Coriolis and do it more conventionally and check your answer, whatever works for you. And so this is just the bottom of my notes here. I'll just bring up. This is just a quick reference for how to get out of Coriolis, and noting you basically simply need to convert stuff to ground. So that's what we're having here. And when you do that, it all works out. So I'll let you study that. And that is all for this problem for now. We still have more Coriolis to do. Catch you next time.